All right, so I've secretly typed in some code to basically drive the inputs of this flip-flop and let us look at the outputs. So we're constructing an instance of a T flip-flop, and I just called my test bed variables exactly the same as the variables in the module we're testing, TFF, just to keep it easy. So clock reset, T, Q, and Q bar. I have another kind of always statement here, always begin. There's nothing that it's asking to be satisfied for this block to fire, right? It's not always at positive edge or at negative edge, it's just always. So this statement is always going to execute, okay? This does not give us hardware, okay? This is a Verilog statement that we're using for simulation. And the way to read this is wait for 10 nanoseconds in this case, because our time scale is nanoseconds. Wait for 10 nanoseconds and then set clock equal to the complement of clock.
Just a quick little, you need a semicolon after the red register.
Yes, I was going to get a compile error and let you see, because there's another one in here. Thank you, though. Good eyes. So after 10 nanoseconds, set the clock to the complement of clock. And then 10 nanoseconds later, set it to the complement again and keep going. Okay, so this is an easy way to say I want the clock to change every 10 nanoseconds. Instead of saying wait 10 nanoseconds, set it 1, wait, set it to a 0, and so on. So I've got a running clock in the background. And then my initial statement is first set the clock to 0 so that it actually has a fixed value. And then 10 nanoseconds later, set reset to 1, set T to 1. Right, and reset and T are registers, so I'm using this notation. And then at 30 nanoseconds, I'm going to set reset to 0. So that should reset our T flip-flop and get it ready to do what it's supposed to do. So I'm going to wait another 60 nanoseconds and then set the T input to 1. Wait another 60, set T to 0. Wait another 60, set it to 1. 60, set it to 0, and then we're done. So we've got a clock ticking every 10 nanoseconds. It alternates between high and low, and we're just driving the T input. And we're going to compile this. We're going to say simulate, and we're going to look at the waveform and see if it does what we're hoping it'll do. And again, this is the module we just wrote for the T flip-flop itself. And it's basically this always block plus 1 assignment for Q bar. So we can compile it up, and it'll give us syntax errors. Right, so the first syntax error is at line 5, and then 50 and 54 and 55. Pick on the first one, okay, because that may take care of some of the other ones. So go down to line 5, and it's complaining about this, and the problem is the line before needs a semicolon. And then don't go on to the other statements. Fix that problem, recompile. So now it's saying line 50. And the problem there is there's no semicolon on this statement. Yeah?
How are you making it jump to 50?
Oh, if you're in VI, you can say 50 and then an uppercase. Well, let's see. It's one of these things I can type, but I can't recall what I'm doing. 20 and then an uppercase G goes to line 20. So line number and then an uppercase G. And if you just do an uppercase G, it goes to the bottom. And I'm in Unix right now, so I'm just using exclamation mark to recall previous commands. So this will recall the last time that I typed something started with an IV, which was my compile command. So it recompiles and compiles without errors now. So now we can say VVP T flip-flop and run that, and it tells me that it created a dump file called tff.vcd, right? And that was right here where I said make a dump file. So I've got my VCD file, so now I can say GTK wave tflipflop.vcd, and there's our wave file window. And up here where it says test bed, I can click on this and I can see the inputs and outputs of my test bed. I can also click on U1 and see the inputs and outputs of those. So I'm just going to stick with the test bed. and I'm just going to drag these over to the signals area. So there's our clock, there's our reset line, there's T, Q, and Q bar. And this red kind of filled in line, which is really hard to see right now, that means that it's an undefined value. I hate blocking out sunshine, especially in the Pacific Northwest. I don't know if that's any better.
It's a little bit better.
Okay, good. So come up here and zoom out, and there's our actual waveform. So the clock is toggling every 10 nanoseconds, and we can put a cursor down here. So this is actually 80,000 picoseconds, or 8.1 nanoseconds. This is 90,000 picoseconds. So these are 10 nanoseconds apart. The reset line was high for a little bit, and then it went low. And the Q output is normally 0. And where's my T input? Oh, my T input's high to begin. Oh, let me change that. Let's make this more reasonable. Let's start off with our T input at a 0. So recompile, rerun, relook at the waveform. So clock, reset, T, Q, and Q bar. Zoom out. All right, so the T input is low, our Q output is low, our Q bar output is high, right? And it's highlighting the values of the cursor here. So this flip-flops in a stable state until we get over here where we set the T input to 1. And we did that exactly as the clock was falling, so nothing happened. But the next time the clock falls is right here, and you can see that Q rises to a 1 and Q bar drops to a 0. And the next negative edge is right here, and Q drops to a 0 and Q bar rises to 1. And then at this point, we set the T input back to 0, and now Q is totally stable at a 1, Q bar stable at a 0, until the T input goes high, and then on the next falling edge, they begin to alternate again. So that's a good T flip-flop. So questions about that? So you got to get in there and you got to be doing this, right? Up to that point, it's theoretical, and it might make sense, but actually doing it is a whole different matter. How many people here are taking physics? Okay, I don't want to bias you, but when I took physics, I had a horrible time with physics. And here's my experience in physics, and if you haven't gone through this yet, that's great, but you may recognize this. I would go to class, and I would listen to the lecture. The lecture made perfect sense. I'd take down notes. I'd follow everything the teacher was doing. No problem. No questions, right? Any questions? No. All right. I'd go home and I open the book to do the homework. Question 1. What the heck is this? I've never seen this before. And I go back to my notes and I try to take what I had seen done on the board and apply it to this problem. No. This was a mistake. This shouldn't have been an assigned problem. Go on to the next question. Same experience, right? And I would just beat my head against it for hours. Couldn't get anywhere. So I'd go into recitation the next day. Any questions? I don't know how to do question 1. Oh, blah, 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 blah. Oh, that makes sense. Okay, I get it now. How about question 3? Blah, 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 blah. Okay, I'm good. Right? And then you go home and the exact same thing happens. Right? So that's how a lot of subjects feel, particularly as you start going up into higher level courses. And it's because there's this fundamental difference between seeing something done and understanding how it's done versus actually going in and doing it yourself, right? You could watch someone do brain surgery and they could explain to you everything that they're doing and it would probably make sense. And then they hand you a scalpel and put you in front of a patient and say, okay, it's your turn. Totally different experience, right? So that's kind of what goes on with Verilog for most people, right? We can talk about the assign statement or the always block, and it might make sense, or you might think about it enough and you know, feel comfortable with that. But when you actually try to write something, it's like, I don't really know how to start. And, you know, I wrote this, but I don't really know what it's doing, and so on. And the only way through that is just to keep doing it, right? We can't do that for brain surgery. But we can do it for Verilog, right? We can write 30 Verilog programs, and they can blow up 30 different ways and give us tons of errors, and that's okay, right? That's how you learn it, right? And you gotta make the mistakes, because that's where you figure out where your misunderstandings are, and that's how you can course correct. So you definitely want to get in there as soon as possible and start trying to do things like the lab, right? And particularly the mood machine when you're ready to work with always blocks. But we made a T flip-flop, right? Let's make a counter. So what does a counter need? We're still going to want a reset input to put this in some initial state. We're going to want a clock, because that's what's going to drive it. Let's give it a go input. So if go is 1, it'll count. If go is 0, it will not count. Okay. And let's do a 4-bit counter. Let's do a 3-bit counter. Just so we don't have to get really wide on the screen.
Why is the bit amount always one more than the number you put so low?
Good question. Because we're starting at 0. So
Oh.
we got wire 0, wire 1, wire 2. That comes up again and again in programming, by the way.
0 is a 1.
Yeah. And 1 is a 2. Alright, so we got a clock, we got a reset, we got a go, which we're just going to call go. And we've got out, which we'll just call out. And we'll leave the clock ticking every 10 nanoseconds, because that seemed to work well. We'll initialize the reset. We'll do go is a 0. Set the reset to 0, and let it clock for a while. Let it stop. Let it clock. Let it stop. And we'll just do lots of. We can zoom in on the display. So we'll just go 600 nanoseconds for each of these and see what happens. So let's make our counter module. So it's got a reset, a clock, a go, and an out. You want to count up or count down? Up. Yes?
Can our so our counter module can go after the test bed?
It can go after. I think it can go before also. I think it'll handle a backwards reference. It can also go in a totally separate file. All right, so reset's a wire, clock is a wire, go is a wire, and then Q is going to be an output. And that's a register. I'm not really doing a whole lot of imaginative to the test bed, right? That just kind of changed some variable names and stuff, right? That's sort of the nature of test beds. So you get yourself some test beds and you can reuse them, because it's really just a way to stimulate inputs, look at outputs. All right, but our counter, we want to do something different. So let's do positive edge. If reset equals 1, force the output to 0. So we'll set out to 0. Else if go equals 1, and we'll just set out equal to out plus 1. have a Q bar to worry about. There's the end of our module. So we just ripped all the wires out of our proto board, and we got 3 flip-flops, and we hooked them up, and we did a state diagram, and we built a 3-bit counter out of this. And does this look right? And I don't know if it's right, so it's a real question. I'm going to make you share the blame if it doesn't work. Reset is 1, set the output to 0. Go is 1, set out to out plus 1. Look good? Good enough to try? Because it's not surgery. It's not brain surgery. Let's see if it compiles. It compiles. It executes. Let's see what we did. Oh. Called my dump file T flip-flop again. I could leave it at that, but it's confusing. So let's call our dump file counter. Let's recompile, let's re-execute. And let's rerun GTK wave. Let's put our glasses on. So we'll get our clock, we'll get our reset signal, get our go signal and our output, and we'll zoom out, and this looks pretty good. All right, so we got our clock, it's oscillating up there, and our output is a nice solid 0. There's a little 0, 0, 0 here in the line, and if I double click on this, we can see each of the signals of that 3-bit bus, and they're all zeros. But then over here, the go input raises to a 1, and now on each rising edge of the clock, our counter counts. So there's a 1, there's a 2, there's a 3, there's a 4, and you can see what the 3 signals are doing, and they're counting in binary. 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. And you can see those values over here. 1, 1, 0, and so on. And it counts up till everything is 1, 1, 1, and the next rising edge of the clock, it goes back to 0, 0, 0. And this continues as long as the go line is high, but then at this point, the go line drops to a 0, and now the count is just stable at whatever its value was. So we made a 3-bit counter. And I can right-click on this, and I can say, let's do decimal. And now it's showing me the decimal value of the count. So we can see it goes 3, 4, 5, 6, 7, 0, 1, 2, 3, and so on. So is this useful? If you're on a desert island and you can barter clocked circuitry for food, it's definitely useful. And the real guts of it again was really just this block of code. Right, so that's the take-home part of this lecture is always blocks. That's what we're talking about. But the ability to put this in a test bed, compile, execute, look at it in GTK wave, right? That's part of the process because it lets you know if your module is doing the thing that you want it to do. And Verilog's pretty smart about stuff, right? So if out is equal to 7 and we add 1 to it, technically out's equal to 8, but it's only got 3 bits associated with it, so it just becomes a 0, and it ignores that 4th bit, right? So that's pretty smart. If we wanted to count by 3s, right? We just changed our circuit around completely. All right, now we got something counting by threes. Let's go 614 7250 3614, and so on. So a counter is a pretty simple thing to describe, right? It was just out equals out plus 1 or out equals out plus 3. But doing an arbitrary state machine is really no more complex. So let's look at the mood machine. So we've got an input W, that was our weather, it's a 1 or a 0. We've got an output Z, which is a 1 or a 0. And we've got 4 states. And we know state machines are clocked on a clock edge. So something like always at positive edge clock. Begin. Well, in words, what do we want to have happen here when the clock ticks? We need to know what state we're in. And based on that state and on the value of the input, we want to set the value of the output and the value of the next state. And so we could do something like we can make a state assignment table. We still got to do that. So state. So it could be very sad, sad, happy, and very happy. And we could give these values of 1, 2, 3, and 4, if we like. And this is saying if our state value is a 1, meaning we're very sad, and our input variable W is a 1, our output should be a 0, and our new state should be 2, which is state S. So let me write that, and then I'll show it to you. So if state is 0, and, sorry, state is 1, that's very sad, and our input W is a 1, then we want our new state to be a 2, and we want our output Z to be a 0. And we could write it something like that. If our state's equal to 1 and W is equal to 1, then set state equal to 2 and set Z equal to 0. Else, if our state is 2 and the weather is 0, then look at your diagram, see what the state should be, see what the output should be, and so on. So we can skip the whole state transition table, the whole setting up with the flip-flop inputs, the equations, the K-maps, all of that, and really just describe almost in words what we want the machine to do based on that state diagram. Now it's a bunch of if statements. It's going to be at worst case 8 if statements. Some of them we don't care about. Those 2 on the end, right, we never actually change state, so we don't really care about these cases. But if you're in this state and your input's a 0, then we want to go to this state and set your output to a 0, and so on. And you write that code, and there's your Verilog module for the state machine. So my suggestion is try to get a counter working, right? Just to figure out the details of the syntax of the always block, no semicolon after begin, and that kind of stuff. And then, I don't know, try to make a down counter that counts down. And then try to make like a counter that goes from 2 to 7 and back to 2. That's a little more involved. It's got another if statement, right? But this gets you more comfortable with putting things in the module inside the always block that change the behavior of the system. And then maybe don't do the mood machine. Maybe design yourself a simpler machine with like 2 or 3 states and make a state diagram and see if you can write Verilog to make it happen. And then go ahead and do the mood machine. Yeah.
So we say that in the first if statement we have 1, if 1 is equal to state and 1 is equal to W.
Mm-hmm.
Do we have to write one for if 1 equals to state and 0 is equal to W? Is that
If you want something to happen in that case, you would need to write an if statement for it.
What if it's going to stay in that state?
If it's going to stay in that state, you don't have to tell it to do anything.
Okay.
It's like if the T input is 0 on the T flip-flop, we didn't say what to do. But you could do that, right? And it would make it clearer and it would make it easier to change. Because then you'd have exactly 8 statements for the 8 possibilities. And you would just say what each one's going to do. And some of the tools that do this for you, I think that's what it would actually come up with. It wouldn't take advantage of those shortcuts. Yeah.
On the experiment, like in the lab, do we gotta have the state assignment, state machine, or what, the transition table, what's it called again?
The big long thing?
Yeah.
No.
Okay.
No. We don't want to go to that level when we're doing Verilog, right? Now we could, but we're not going to use that information. And really the idea is not to think about how to take those things and translate them into Verilog. The idea is to think in Verilog, right? And that's the long-term, one of the long-term challenges, is to be able to look at this, right, and just think of this. And it's where it gets to be really fun, right? Because you can, it's like working in a programming language. Here's what I want the machine to do, bang, 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 now it does it. And this is not exactly what an actual state machine looks like, right? Remember, a real state machine is a bunch of flip-flops and some combinational logic. So if we were to do this in that style, this code would look fairly different. We have basically a bunch of assign statements that give a value to something like next state based on the current state and the inputs. And then we have an always block which says when the clock ticks, set state equal to next state and set output equal to next outputs and so on. But this to me comes more directly from this, right? And so that's the way I invite you to think about it. But I'm just saying there are other ways to do this. And this might not be the most directly mapped way from what we've been doing, but that's okay. All right, ready to go on to the weird stuff? Semicolon. All right, suppose A, B, C, and D are just registers. And we say always at the positive edge of the clock begin. A is assigned from B, B is assigned from C, C is assigned from D. So we've got something like flip-flops for A, B, C, and D. And suppose that these are the current values of A, B, C, and D. And suppose the clock ticks, we hit the positive edge, and so now this block of code is firing. So what's going to happen? How are these variables going to change? A becomes a 0, right? A gets the value of B. What else? B comes from C, which is still a 0. C becomes a 1. D, we don't know what happens to. It's just a D. Is there a physical way to describe what just happened succinctly? Yeah, we just did a shift, right? This bit value got copied over to here, this got copied here, this got copied here. This is how you can make a shift register. So I don't think we talked about shift registers. It's another one of these blocks like a multiplexer or a decoder. It's basically something that holds a bunch of bits, and each time the clock ticks, all the bits move down one position. And each time that this happens, there's some bit that falls off the edge, right? And that's usually the output of the shift register. And there's also an opening in the beginning, because you move things down. That's the input to the shift register. So you made a 2-bit version of this for your traffic light lab, right? It was a delay circuit is what we called it, but it was basically a shift register with 2 bits. So this is one way to implement a shift register. This is how you make a digital delay circuit too. If you do music effects and you have a digitized signal, you can take it, turn it into a stream of 1s and 0s, feed it into a shift register, tick it every millisecond. After 1,000 ticks, the thing you put in here a second ago comes out the outside. Convert it back into an analog signal and you've got a delayed version. Pipe it back around and feed it in, you've got a reverb unit. So that's how you can do digital reverb and echo. So let's look at a different version of this. Let's comment this out. And let's do the following. And let's go back to our original version. So now what's going to happen when this clock fires? We get the positive edge of the clock.
Shift down.
So what's going to happen step by step?
D turns to 0. C stays the
Well, D
same.
doesn't get assigned to any from anything, right? So we don't know what D does, but what happens to C?
Turns to 1.
Turns to a 1.
B
And what happens to
turns
B?
1.
B gets copied from C. And what about A?
Stays the same.
Right, it gets copied from B. But that's not what happens. Now that's exactly what would happen in a programming language. Because a programming language is sequential. First we take D and we copy it to C, then we take that value of C, we copy it to B, then we take that value of B and copy it to A, and at the end A, B, and C are all equal to D. Got a bunch of 1s. Okay, that's perfectly correct for a sequential language. Verilog is not a language. Okay, this is not a sequence of operations, this is a piece of hardware. So let's see what this hardware actually looks like, and then we'll see what this actually does. So we're going to have flip-flops. And they're possibly just D flip-flops. So that's a D is a data input, it's not the D in our Verilog code. And let's suppose that this is where we're storing the value of D and C and B and A, just so I don't have to cross too many wires. So what is this statement doing? Well, this is saying all of these clocks should be tied together, right? Because we want everything to happen on the common clock. So this is saying when the clock ticks, we want to take the value of D and we want that to become the new value of C. How do we do that? We take the D flip-flop's output and we feed it to the D input of the C flip-flop. And we want C's value to get copied into B, so we take the Q output from the C flip-flop and feed that to the input of the B flip-flop. And we want B to get copied to A, so we take the B flip-flop's output, feed that to the input of the A flip-flop. And so initially we had A was a 1, a 0, a 0, and a 1. So now looking at the circuit, what happens when the clock ticks? Positive edge. What's the new value of C? That's absolutely going to become a 1. But what's the new value of B when the clock ticks? It's a 0, because when the clock ticks, the D input was a 0. D input is 0, tick the clock, output is a 0. And over here, the D input was a 0, clock ticks, the new value is a 0. And so we've still got a shift register. And this is, for me, this was the most mind-boggling aspect of Verilog, is that this and this do exactly the same thing. And from a programming perspective, this and this do very different things, right? This makes everything a copy of D, this moves everything down one position. But it's not a procedural language, it's a hardware description, and hardware is parallel. Okay, this is the aspect that makes hardware the future. Software is fundamentally sequential, hardware is parallel. Guess what? The universe is parallel. So what's the best way to model and interact with the universe? Hardware. And this is why FPGAs have become such a popular way to do computing. Because you can have 128 cores in your very expensive processor and do 128 things in parallel. The chip inside my phone is doing a few billion things in parallel. Right? Every transistor is acting independently of every other one at the same moment. And that's just this huge untapped potential for computing and processing. So that's what FPGAs are tapping into. And this is why when people started doing, how many people here know about bit mining? Right, so Bitcoin, digital currency, and you've got to figure out new pieces of currency by basically mining for numbers with certain properties related to primes. And when people started bit mining, right, they weren't doing it with programs, they were buying FPGAs and building circuits to do it because it's just so much faster. And so all of a sudden Amazon had tons of FPGA kits available and everybody became an FPGA programmer for a few years until there was no more mining left to do. Because all the easy stuff got picked.
Is that what the mining specific cards are? Is just
Probably, yeah.
buffed up, fully programmable?
Yeah, probably. Because to make custom chips is really expensive, right? It's millions of dollars to make a custom piece of silicon. But you can get pretty much the same performance, maybe a little bit lower, using an FPGA. And FPGAs are cheap. Well, some of them are cheap. So you're on the forefront of a wave, in my opinion, of future technology if you're doing hardware design and you're dabbling in Verilog and looking at FPGAs, right? I think it's really a direction that the industry and the market space is moving, because it's just the beginning too. All right, so so one of the take-homes from this, right, it's useful sometimes to think back to what your synthesized hardware looks like. You write this and it's not doing exactly what you thought it would do. Think about what the compiler is going to do. What kind of hardware is it going to build? And this is where I need to introduce some forbidden knowledge. And it's forbidden because once I introduce it, it may be misused. So these things, these are called non-blocking assignments. Non-blocking means this assignment does not have to wait for the previous assignment to finish. Okay, now in a programming language, all of our assignment statements, basically we can think of them as blocking because this statement will not happen until the previous statement has completed. Right? And that's important because if we wrote this in C, we would want B to take on the value that C got in this previous statement. But in Verilog, when you use this less than or equal assignment statement, that's called a non-blocking assignment. But there is a blocking version. Okay, and I'm going to put this in a bubble and label it no. But we can say y equals x, and that's a blocking assignment. And here's why it's dangerous knowledge, because most of the time if you do this instead of the non-blocking, your code will still work. But then at one point it will stop working. And you've been doing this for a week, and the problem is you needed to do this, and you came across a situation where it makes a difference, for example, these two. Because if I write this with equal signs instead of this non-blocking assignment, then we get that behavior that we first thought about, where everything ends up being the value of D. Because it forces it to do things sequentially, this, and then this, and then this. And for what we're doing in here, you don't need to use these blocking assignment statements, and I suggest you totally avoid them. Okay? But I mention them just because if you forget to put the less than sign, and you do one of these, you won't get a compile error. Okay? But if you're getting weird behavior, go back and make sure that you're using non-blockings. Okay? So for an assign statement, we assign y equals x. Inside an always block, we say y less than equals x, right? The little arrow symbol. So that's a gotcha to keep out an eye for. So questions? All right, so that's plenty of stuff to chew on for the next few days. So try to get your lab done by Thursday, okay? It's an ambitious lab because Verilog is, a whole different thing. But try to get it done by Thursday, and if you can't get it done, bring some questions, okay?
Can you change it to be by midnight on Thursday?
I'm going to be, I shouldn't say this, I'm going to be generous with late submissions for Lab 7, but I won't say how generous, so don't be tempted to start it next week. But yeah, if you get it in by midnight, that'll be fine. But then Thursday, we're going to talk about Lab 8, which is optional, but we're going to start talking about working with FPGA. So we're going to take the Verilog that we've got so far, and we're going to look at a different tool chain instead of Icarus Verilog. We'll look at some Xilinx tools, and we'll see how to take this and use it to actually configure a physical piece of hardware, an FPGA, to do whatever our module says to do. And we'll use that to make some lights turn on and off or do some logic or things like that. And that'll be kind of on top of everything we've done, but sort of a separate topic by itself. All right, so I will see you on Thursday.